So welcome all to week 5 tutorial for the course Deep Learning. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So today I'm going to cover these topics that were covered in week 5 of the course. So first I'll begin with eigenvalue and eigenvectors. I'll do some examples on how to find eigenvalue and eigenvectors. I'll try to briefly motivate you what is eigenvalue and eigenvector. Then we'll do some examples based on principal component analysis, and then we'll try to do example on similar value decomposition. We'll try to go fast so that we are able to cover everything. Anytime during the lecture, if you have any doubt or you want to ask anything, you can simply unmute yourself and ask then and there, or you can even type it in the chat box. I'll be monitoring the chat. Okay, so yeah. So I'll begin. So most of this week's lecture revolved around eigenvalue and eigenvector. I'll try to motivate it from a sort of mathematics perspective. So let's say you are given with just two system of equation. Let's say this is x plus y is equal to 2 and 2x minus y is, let's say, 1. And you are given with another system of equation where you have 0x plus y is equal to 1 and x plus 0y is again equal to 1, right? So which one of these system of equation is easier for you to solve? So like both of them are quite easy, but like if you are given some complex system, when you have only diagonal entries available, then that kind of system becomes easier to solve. Okay, so if you have a matrix A in which your matrix representation you have entries only on diagonals and everything else is 0, that kind of solving that kind of system of equation is much easier. Okay, so whatever we did in the course was from sort of a deep learning perspective. I'll just take a very small detour. And so how did linear algebra people motivated this diagonalization and eigenvector is, so for any given linear transformation, what they wanted to do is they wanted to find a basis beta such that the matrix representation of that transformation that they are getting should be diagonal. Okay, so now the question is whether this kind of basis always exists, and the second question is, if it exists, how do we find it? Okay, so I'm not going to answer the first question whether it always exists or not. The answer is it won't always exist. But when does it exist, when it does not exist, that you can sort of do in some linear algebra course, not today. But I'll sort of try to find whenever it exists. Okay, so yeah, any doubt till this point? Okay, so what we want is, so let's say if T is your linear transformation, or you can say how does a linear transformation looks? So if you have a matrix A corresponding to this T, so every linear transformation corresponds to a matrix and every matrix corresponds to a linear transformation. So AX is your linear transformation. Okay, so whenever I say linear transformation, it is nothing but matrix A multiplied with a vector X. Okay, so what we want is that whatever Ax we should get some lambda times X. Why do we want this? Because we want this matrix to be whatever the output matrix that we are getting to be a diagonal matrix in terms of these X vectors. Okay, so what we want is that this X should be scaled by some factor lambda. So this is the only property that we want, and we want to find a set of linearly independent vectors X satisfying this kind of property. So this lambda need not be unique, this lambda can be different. So let's say you found a set of vector x2 to xn, you can have ax1 is equal to some lambda 1 x1, ax2 is equal to some lambda 2 x2, and so on. Okay, so this is what we want to find. So how do we find? So we solve this system of equation. Okay, so from I have written it in terms of t of x over here. I'll now switch to a of x. So let's say if you want a of x is equal to lambda x, what we can do, this is similar to saying that ax minus lambda x is equal to 0. Okay. Remember here 0 is not your scalar 0, but a vector 0. Okay. Okay. Yeah. So if we take our x common, what does this lead to? A minus lambda I times of x is 0. So if you want to find the now, okay, so one important thing that I missed is if your ax is equal to lambda x, then this lambda is called the eigenvalue and your x is called the eigenvector. Okay. So this is the definition for eigenvalue and eigenvector. And one more thing, your x should be non-zero. Okay. Because if your x is 0, then a times 0 is always 0. Okay. So it has, it corresponds to many eigenvalues. And this is not an interesting case that we are interested in. Okay. So we want our x to be non-zero and we want it to satisfy ax is equal to lambda x. Your lambda is called as eigenvalue and your x is called eigenvector. Okay, and how do we find it? We just took lambda x to this side. So first step would be to find eigenvalues. So how do we find eigenvalues? We find eigenvalues by this system of equation. Okay, so we want to find all the solutions of lambda such that a minus lambda I x is equal to 0. Okay, then we'll find eigenvectors accordingly. Okay, so let's do a very simple example, then we'll see a complete example where finding eigenvalues and eigenvectors. Okay, so in this question you are given with some a, okay, and you are also given with two vectors v1 and v2. Your role is to check if v1 and v2 are eigenvectors. Okay, so first question is this, and second is if v1 and v2 are eigenvectors, then find corresponding eigenvalues. Okay, so what do we want to happen? So if let's say my v1 is an eigenvector, what should happen? If v1 is an eigenvector, then a times v1 should be some lambda times of v1. Okay, so it should be just scaled by some factor lambda and its direction should not change. Okay, let's calculate what is a times v1. So this is 1 3 4 2 times 1 minus 1. This is nothing but 1 minus 3 is minus 2. This is 4 minus 2 is 2. So can it be written into something multiplied by v1? Yes, it can be. This is minus 2 times 1 minus 1. So what did we infer? v1 is an eigenvector with eigenvalue equal to minus 2. So this is the factor by which this thing was getting multiplied after we pass it through the matrix A. So this is my eigenvalue and this is my eigenvector for this particular matrix. Let's check for the another one also. So let's say for v2 what we do, this is 1 3 4 2, this is 3 4. Okay, so this is 3 and 12, this is 15. Okay, this is 12 plus 8, 12 plus 8 is 20. Right, I think I have done the calculations correctly. So this is 3 plus 12 is 15, 12 plus 8 is 20. So can we write into some lambda times 1 comma minus 1? So this particular relation is never true for any lambda, right? For no lambda, this is true. So V2 is not an eigenvector. So 5 would mean, if you take 5 common, this would mean 3 comma 4, right? But we want something of the form that it whatever we take out common, then we should, whatever is left over here. So the term left over here is 3 comma 4, right? Sorry. Term left over here is 3 comma 4. What we want is the term that should be left is 1 comma minus 1. That is not possible. Okay, so we should have obtained something like, yeah.
It is, we are doing it for V2, but V2 is 3 and 4.
Right. Oh, I'm really
So
sorry. Yeah. Yeah, I'm sorry. I'm sorry. Okay. Yeah, I'm really sorry. I just thought that we are doing for V1. Right, I'm sorry. So correct. Whoever raised this question is absolutely correct. So what we are doing is, this is 5 times of V2. So V2 is also an eigenvector. I'm really sorry for this. Vector. And the corresponding eigenvalue is 5. Okay. So yeah. Okay. So this is fine. Okay. So right. Okay. So we have one more question over here, where we'll try to find eigenvalue and eigenvector from the scratch. So in the previous part, we were given with 2 vectors and we had to verify if it is a eigenvector or not. Okay. Now the question is, you are not given anything, you are just given with matrix A, and you have to check, you have to find all the eigenvalues and corresponding eigenvectors. Okay. So we will try to solve this. Any doubt in the previous part because of the last moment change? There might be some doubt. Any doubt? Okay. So what we want is, we want again AV is equal to some lambda times V. As I mentioned, this is similar to solving A minus lambda I, V is equal to 0. Okay. Now, whenever you have to find eigenvalue, okay, what you want is, so whenever, I think if you did some linear algebra course, then when solving system of equation, let's say mx is equal to 0, okay, if your M matrix was full rank, okay, or I can say, let's say if, or what I mean is, if let's say determinant of M is non-zero, okay, then what will happen is, then my M matrix is invertible, right? Let's say if I am trying to solve mx is equal to 0 and my matrix M is full rank, or it is similar to saying that my determinant of M is non-zero, then what does it mean is that my M is invertible. Okay, so if my M is invertible, what does that mean? That my x is equal to M inverse of 0, which is 0. So if my determinant of M is non-zero, the only solution that mx is equal to 0 can have is x is equal to 0. Okay. Now, when we are trying to solve for eigenvectors, then what we want, that our V should be non-zero, right? This is the condition for our eigenvector. So what we want is, the matrix that we have over here, that is A minus lambda I, its determinant should be 0. Then only it can have some non-zero solutions. Okay. So first step when you will solve any eigenvalue problem is, what you will try to do is, you will try to do the determinant of A minus lambda I is 0. Okay. Now what is my A over here? A is 1 comma 1. So what we will try to solve is 1 minus lambda 1 4 1 minus lambda is equal to 0. So how did we reach here? This is nothing but this is 1, 1, 4, 1 minus this is lambda I, right? 0 lambda. So if you subtract, you will get 1 minus lambda, 1 minus lambda, 1, 4. Okay. So this is what we want to solve. Okay. So this is nothing but 1 minus lambda square minus 4 is equal to 0. This is lambda square plus 1 minus 2 lambda minus 4 is equal to 0, which is equivalent to saying that lambda square minus 2 lambda minus 3 is equal to 0. Okay. So this is lambda square minus 3 lambda plus lambda minus 3 is equal to 0. This implies lambda minus 3. And what is my second factor? This is, I think, a lambda plus 1. Right? Yeah. So I'll take lambda common over here, lambda minus 3. Yeah. So what does this mean? This gives lambda is 3 or minus 1. So 3 and minus 1 are my eigenvalues for this particular matrix, whatever was given. Okay. So any doubt till this point, how do we find eigenvalue? Why did we did determinant of a minus lambda is equal to 0 or anything? Then we'll proceed to find eigenvector.
Sir, why you have changed minus 2 lambda to minus 3 lambda?
Okay, so I just wanted to factorize this thing.
Oh, okay, okay,
So
okay, sir.
minus 3 lambda plus lambda.
Okay, sir.
Okay. Okay. So this is how we find eigenvalues, right? Now we have to find eigenvector. So when you are finding eigenvector, that should be corresponding to some eigenvalues. Okay. So first we will find eigenvector for lambda is equal to 3. Okay. First we will do this. Then we will do for lambda is equal to minus 1. Okay. So now again the same criteria that a lambda a v should be equal to lambda times v, or a minus lambda I v is equal to 0. So lambda over here is 3 now. So what we want is that a minus 3I times v should be equal to 0. Okay. So what was my a? A was 1141. So 1141, I think this is correct. Yeah. Minus 3I. So minus 3I would mean that this term would become minus 2. This term would become minus 2. Right. And this is my vector v. So this is v. And I want this to be 0. Okay. So what does this gives? This gives minus 2v1 plus v2 is equal to 0, or v2 is equal to 2 times of v1. Okay. So one thing you should remember is, let's say my mu is an eigenvector with eigenvalue lambda, then 2 mu is also an eigenvector with eigenvalue lambda. Similarly, 3 mu is also an eigenvector. Similarly, 1 by 2 mu is also an eigenvector with the same eigenvalue lambda. Or you can say that C mu is an eigenvector with the same eigenvalue lambda. Okay. So what I'm trying to say is, whenever you try to find some eigenvector, you don't get only one eigenvector, but you get a complete space of eigenvectors. Okay. So what we eventually choose is, we choose the basis vector for this span, whatever we are doing. Okay. So for example, in this case, let's say if we take our v to be 1 comma 2. So this satisfies that my v2 is 2 times of v1. Okay. So this particular vector spans all the vector that would satisfy this condition, right? So this can be chosen as an eigenvector. Similarly, you could have chosen any eigenvector, right? You could have chosen half comma 1. Okay. So you could have chosen any eigenvector. So right now I am choosing v is equal to 1 comma 2. But you should choose only one out of it. Okay. Now let's try to find eigenvector for lambda is equal to -1. Okay. So for lambda is equal to -1. So this would give 1 1. This was 4 1. This minus minus would become plus, and this would give 1 0 0 1. This time v is equal to 0. This implies nothing but 2 1 4 2 is equal to v is equal to 0. Or if you do similar thing, you will obtain 2v1 plus v2 is equal to 0, which is similar to saying v2 is minus 2 times v1. So you can choose your v here to be 1 comma minus 2. Okay. So in this example, you had two eigenvalues, 3 and -1, with corresponding eigenvectors as 1 comma 2 and 1 comma minus 2. Any doubt on finding eigenvalues or those kind of things? Because PCA and singular value decomposition all will be based on finding eigenvalues and eigenvectors. Okay. So there is a question related to sum and product of eigenvalues in the assignment. So that's why I have included. So let's say you have a matrix A, right? And you have corresponding eigenvalues as lambda 1, lambda 2, lambda n. Then the sum of eigenvalues, is nothing but the trace of your matrix A. What is trace? Trace is sum of diagonal elements. So in the matrix, if you just sum all the diagonal elements, then you get the trace of that particular matrix. Okay. So this is one property. Another property is if you take product of all these eigenvalues, you get determinant of your matrix A. Okay, I'm not going to prove it, I'm just going to state it. We can verify it with the last example that we had. So here you had A is equal to 1 1 4 1. So the eigenvalues that you obtained were 3 comma minus 1, right? If I'm not wrong, yeah, 3 comma minus 1. If you take yeah, sum of these eigenvalues, what is the sum? Sum is 2. So you can check if you take sum of the diagonal elements, that is your trace. So trace is equal to the sum of eigenvalues. Now the product is equal to -3. You calculate the determinant over here. Determinant is 1 minus 4 is equal to -3. Okay. So it is true for any arbitrary matrix. Okay. So this you can use. Okay. Now we'll go to something called spectral decomposition or eigen decomposition. Okay. So these are same things but different name for the same things. So let's say if A is your square matrix, okay, the first condition is that if A is your square matrix and it has n linearly independent eigenvectors. For example, in the last example, we had 2 cross 2 matrix and we had 2 linearly independent eigenvectors. So it is true only for those kind of matrix. Let's say you have n linearly independent eigenvectors, then you can write your matrix A in form PD P inverse. Okay, what are these P and what is this D? So what is this P? In P, you have stacked your eigenvectors in form of columns. Okay, so the column of T are eigenvectors of your matrix A. Okay, and what is your D? D is a diagonal matrix with eigenvalues on the diagonal. So this is lambda 1, lambda 2, lambda n, and 0 elsewhere. So this is what a diagonal matrix looks like. Remember that this, if you have written lambda 1 on the first position in the D, then you should include the corresponding eigenvector in the P matrix. You should not do like you have included, let's say, in the last example, you have written D as 3 minus 1 0 0, and here you include in P the eigenvector corresponding to V1 first, and then you include the eigenvector corresponding to V3. Okay, V minus 1 first and then to V3. This won't help. Okay, so to write an eigen decomposition, you should first you should maintain the order in which you are writing both the matrices. Okay, so one very small thing is that this kind of calculation is very useful in calculating the powers of matrix that can occur in many different like applications. So let's say if you want to find a to the power 50, right, what you can do is, okay, let's say we just begin with a square. So a square is p dp inverse, p dp inverse, right? So this p and p inverse becomes identity. So you would be left with p d square p inverse. Now if you have a diagonal matrix, let's say your D is lambda 1, lambda 2, 0 0, then D square is nothing but lambda 1 square 0 0 lambda 2 square. So you just square your diagonal entries and you will get D square. Similarly, if you have D cube, these terms will become D cube, and this is true for any n cross n. Right now I have just given you example of 2 cross 2. This is true for any n cross n. Okay, so similarly, if you want to find a to the power n, this is p d to the power n p inverse. So once you have calculated the p and d matrices, then you can use this to find any arbitrary power of your matrix A. Okay, this is one thing. Another important thing that I want to mention is, if you have a symmetric matrices, what is a symmetric matrix? Symmetric matrix is a matrix for which A transpose is equal to A. So if you have a symmetric matrix, then your eigen decomposition always exists. So you can always find n linearly independent eigenvectors, and you can write your matrix A in form of P D P inverse. Okay. Okay, so I have purposely included this question. So I'll give you some 5 odd minutes to solve this question. So you are given with a matrix A, you have to find the spectral decomposition, or you have to find the eigen decomposition, whatever you want to call it. So what would you do? First you will find the eigenvalues, and you comment or unmute and say what are the eigenvalues that you obtained. Then you find the corresponding eigenvectors, and please let me know whatever you obtain. Then we can use to match whichever option is correct. If we have P and D available with us, then we'll match whatever option is correct. Can you please guys find eigenvalues and eigenvector for this particular matrix? I won't ask you to do it for the rest of the questions, but for one question you should try and solve it on your own, so that if you encounter any doubt in between, we can clear it right now. Okay, so yeah, you should try finding eigenvalues and eigenvector. Can you please let me know what is eigenvalue? I'll wait till 6:40, so you guys can try, because this might include some calculations. So I'll wait for some calculations. Okay, one more very small thing. So you can continue doing this, but one very small thing. So if you have symmetric matrix, so the eigenvectors that you obtain are also orthogonal in nature. So are also orthogonal in nature. So what does two orthogonal matrix means? So if you have xi and xj, then xi transpose xj is 0. This is what is meant by orthogonal. So you can again make it ortho. So there is one more term in linear algebra that is known as orthonormal. Orthonormal. So what is orthonormal? Orthonormal vectors are orthogonal plus normal vector. So orthogonal plus unit vectors, I would say. So you satisfy this particular property, plus you have that norm of xi is equal to 1, which is again norm of xj. So their length should be also 1, and they should be perpendicular to each other. These kind of vectors are called orthonormal vectors. Okay, so you can continue doing this question. I'm expecting eigenvalues for this particular.
5 by 2 and comma 1 by 2.
So the eigenvalues that you are getting is 5 by 2 comma 1 by 2.
Yes,
I'll
sir.
wait for others also to verify. Somebody
Yes,
says
sir.
1 and 5. So yeah, we have got two different sets of answer. So let's see what others also get. Okay, somebody else has also 1 by 5. So two people have said this, one people has said this. Okay, I'll wait for one more minute. Then probably you can. Okay, I also think that 1 and 5 is the correct answer. I am not explicitly solving it, but if we look at all the options that are given, the diagonal matrix will have eigenvalues on the diagonals, right? So all of them have answer 5 and 1 only. So I think 5 and 1 is the only possible thing that we should. So we can explicitly solve, but we won't solve. I would go with 5 comma 1. So you can try finding eigenvector and let me know which is the correct option among these. So I'll probably solve for lambda is equal to 5. So for lambda is equal to 5, okay, for lambda is equal to 5, so a minus 5 pi b is equal to 0. This implies, I'll change the color so that you don't confuse here. So this is 3 minus 5 is minus 2, comma 2, 2 comma minus 2. This v1 v2 is equal to 0. So this implies minus 2 v1 plus 2 v2 is equal to 0, or v1 is equal to v2. So when my v1 is equal to v2, one best option that I can have is 1 comma 1. What next I can do is I can just find the orthonormal sort of vector. So I'll just divide it by 1 by the norm of this vector, that is 1 by root 2 and 1 by root 2. What is the advantage of doing this is, so if you have an orthonormal matrix P where every vector is orthonormal, then P inverse is nothing but your P transpose. So finding the second part will become very easy if I write it in orthonormal form. So my first vector should be 1 by root 2 and 1 by root 2. So either this option should be correct or this option should be correct. You guys please calculate it for lambda is equal to 1 and let me know which of these options is correct. Okay. So you guys can calculate the eigenvector for lambda is equal to 1 and tell me what you obtain, and we can take a correct answer accordingly.
V1 equal to minus V2, sir.
Okay.
For lambda
equal to minus V2.
equal to minus V2.
Right. So others can also try and see if this is what you are getting. Okay. So I think this is correct. So I'll just solve, right? So the matrix is 3, 2, 2, 3. So if I do minus identity from here, I'll get 2, 2, 2, 2. So I want to solve 2, 2, 2, 2. V1, V2 is equal to 0. So this implies that 2V1 plus 2V2 is equal to 0, or V1 is equal to minus V2, what was mentioned by somebody. Okay. So we can have a 1 comma minus 1, or we can have a normalized form, which is 1 by root 2 comma minus 1 by root 2, or we could also have a minus 1 comma 1, which has generalized form minus 1 by root 2 comma 1 by root 2, right? These are the scalar multiple of each other, so it doesn't matter a lot. So this is the option where we have such matrix. And if you see, the inverse that they have calculated is just the transpose of this matrix. So if this is P, this is just the P transpose over here. Okay. Okay. Okay, so I'll skip this question because I want to cover some more content. If we have time left towards the end, we'll get back to this question and we'll try to solve this example also. So question is, can we always find an eigen decomposition? Okay, so we are given with a matrix where we have this you consider this to be A, and forget whatever is written over here. Okay, so we have to find the eigenvalue and corresponding eigenvector for this particular. Okay. I'll quickly try to solve this thing. Okay, so if I have A minus lambda, okay, so one very simple trick that I want to tell you, you can use it or you can even ignore it. Let's say if you have a upper diagonal matrix, let's say you have x1, x2, x3, you have some x4, something over here, and 0 everywhere. So this is something that is called as upper triangular matrix. Then your eigenvalues are nothing but the diagonal entries of this matrix. Similarly, if you have lower triangular matrix, then also this thing is true. Okay. So for example, in this matrix, all the diagonals are 0. So your eigenvalues is nothing but 0, 0, 0. Okay. So we'll try to explicitly solve also. So this is A minus lambda I, determinant is equal to 0. This is what we do to solve eigenvalues that you might have seen while you were doing this last question. So this is minus lambda 1, 0, minus lambda 2, and minus lambda, and 0 everywhere else. Okay. So this we want to be 0. Let's solve along this column. So this is minus lambda, right? This is how we calculate determinant. This is lambda square minus 0, right? From here we get lambda square minus 0 is equal to 0. This simply implies that minus lambda cube is equal to 0, or lambda is 0, 0, 0, right? So we have only one eigenvalues, lambda, with multiplicity 3. So that particular eigenvalue is getting repeated 3 times, okay, because we had lambda cube over here, okay. So we have to find the corresponding eigenvectors. So now for lambda is equal to 0, a minus lambda I v is equal to 0. What does this imply? So my lambda is 0, so I would just have av is equal to 0. So what is my a? A is given to be 0, 1, 0, 0, 0, 2, 0, 0, 0. Now this vector will have 3 components, that is v1, v2 and v3. This thing is equal to 0. This would imply that my v2 is 0 and v3 is 0. So whenever you did your linear algebra course, so you have 2 variables fixed now. The 2 variables can have only 0, 0 values. So you have only one free choice. Okay, so you can place a 1 over here. So what does this mean is the eigenspace that we get corresponding to lambda is equal to 0 have dimension equal to 1. Or you can say that you only got one linearly independent eigenvector over here. Okay, so if you come back to what I said for eigen decomposition, if A is an n cross n square matrix and you have n linearly independent eigenvectors, then you can transform this into this form. Now because this matrix had only one linearly independent eigenvector, you can't decompose it as an eigen decomposition. So this is the point that I wanted to make. Okay. Any doubt till this point? Then we'll move to something known as principal component analysis. Anything that you want to ask? Okay, so before going into covariance, just a very, very small recap. I think you all might know what a mean is, but I'll just mention it for your reference. So let's say you have data points x1, x2 to xn. Then the mean, let's say this is feature x. Then the mean of x represented by mu of x is nothing but summation of xi divided by total number of points. You also call it average, okay, or mean, and it's represented by mu of x. Okay, you also might have heard of something called as variance. Your variance is nothing but 1 by, so this is sigma square is nothing but 1 by n summation I is equal to 1 to n xi minus mu x whole square. This is your variance represented by sigma square. Okay, so there are two definitions of variance when you want to find the variance of some population. This one is called as the biased estimate, and if you just divide it by 1 upon n minus 1, that particular estimate is called unbiased estimate. So you might use some based on your application. Somewhere you might use this one, somewhere you might use this one. Okay. So these are two estimates for your variance. And square root of variance, right, is called the standard deviation. And is represented by sigma. This is a very, very small recap that we had about what we are going to use. Okay. Now, when you have a data set with you, you might have some features in it. Let's say your data set has 2 features. You want to see how related your data points are with each other. Okay. So what you do is you define a term known as covariance between x and y. So covariance is always between two random variables, let's say x and y. So how is it defined? So it is defined as summation of x minus mu x into y minus mu y. It is similar to your variance that was defined. So in variance you had x minus mu x into x minus mu x. Now one of the x minus mu x is replaced by yi minus mu y. That's why it is known as covariance. Okay. So and you divide it by n. So one interesting thing is, if your covariance is high, that means your two data points are very much similar to each other. If it is negative, then also it is sort of opposite direction to each other. When it is 0, that means it is like the data points, these data features are not related to each other. Okay. You can take an example. Over here your x is 1 comma 3 and y is 2 comma 4. So what is mu x? Mu x over here is 3 plus 1 by 2 is 2 and mu y is 3, right? So you can find the covariance between x and y as 1 by 2, right? So x minus mu x is minus 1 and x minus mu y, sorry, yi minus mu y is minus 1 again, right? And then we want to add the second term. This is 3 minus 2 is 1 and 4 minus 1 is 1. So this is 1 by 2 times 2. So the covariance between x and y is given as 1 over here. So you can also see, like, if x is increasing, your y is also increasing. So your x and y features are sort of related. That's why we got a positive value. And yeah, that's the way to look at the covariance. Okay. Now, if you had two variables, then it was okay to look at just the covariance between x and y. Sorry, I'm saying variable, it means features. Now, if you have, let's say, a data point where you have multiple features, let's say x1, x2, xn, these are the features, then what you are interested in is something known as covariance matrix. Okay. So how is your covariance matrix given? Covariance matrix is I'm writing over here. This is covariance between x1 comma x1, then covariance between x1 comma x2, and so on. Next row will have covariance between x2 comma x1, covariance between x2 comma x2, covariance between x2 comma x3, and so on. Okay, this is something that is known as covariance matrix. Okay, one interesting feature, let's say if your features x1, x2, xn are such that the mean of these x1, x2, xn is 0, then if, let's say, your x is x1, x2, xn, then the covariance matrix is given by x transpose x. Okay, this is an important thing to remember. If mean of every column is 0, even if it is not 0, let's say for some data set the mean is not 0, you can find the mean and subtract it from every column. Okay. Yeah, the covariance matrix would be symmetric because you have x2 comma x1 and x1 comma x2 over here, so it would be a symmetric matrix. And that's why if you will look after a few minutes, we will do eigen decomposition of this. And as I mentioned, for any symmetric matrix, eigen decomposition always exists. Okay. Okay, so we are given with a data matrix. So here you imagine this matrix as this is your x feature, this is your y feature, and they want you to find the covariance matrix. Yeah, it is the variance of the column. That's what I have written over here. So this is the variance of x1. This is the variance of x2. Okay. Covariance of x1 comma x1 is just the variance of that particular, right? But like if you don't have to explicitly calculate, the best trick is to convert these columns to zero mean and then just do x transpose x. That would be much better. Okay, so here what is the mean of the first row? This is 3 plus 1 4 minus 3 1 minus 1 is 0. Again here also, so the mean is 0 over here, right? So what we will do is to find the covariance matrix, we'll just do C transpose C. So this is 1 minus 3 3 1, 2 minus 2 1 minus 1, and minus 1 minus 3 3 1, 2 minus 2 1 minus 1, right? So I'll explicitly write the first term, so that you can verify that this is indeed what we want. I'll just create some extra space over here. Not working. I'll just erase this and create some extra space. I think it's still not working. Okay, just ignore whatever is written over here for the meanwhile. Okay, so this is principal component. Sorry, I don't know why it is not shifting downward, but just ignore it for the time being. Okay, so what is this? So this would be 1. Okay, so this should be minus 1 over here also, right? This should be minus 1 into minus 1 plus minus 3 into minus 3 plus 3 into 3 plus 1 into 1. Okay, this is the first position. Now, if you look at this particular position, there will be something over here and there will be something over here. Let's find this thing. Okay, so this is 2 into minus 1 plus minus 2 into minus 3 plus 1 into 3 plus 1 into 1. So what we wanted over here was covariance of x comma x, or the variance of x. Okay, so if you have zero mean, what would variance of x look like? So variance of x is nothing but summation 1 by n, right? Yeah, so there will be 1 by n term also over here, that I can't forget. So there would be 1 by n term over here. Okay, so yeah, so what will we do is, just give me a second. Yeah, so what will we have? This is x minus mu x whole square. Now mu is 0, so this is just 1 by n summation of x square, right? That's what we are doing, right? We are summing 1 square plus 3 minus 3 square plus 3 square plus 1. Again, when you have covariance of x1 comma x2 comma x1, that I have written over here, because the mean is 0, this would be sum of xi comma yi, xi into yi, right? You just look at this formula and your mean is 0, so this is summation of xi into yi, right? And that's what is happening. The first term is getting multiplied with the first term, the second term is multiplied by second, third by third, fourth by four, and we are just summing it up. So this is how you can obtain the covariance matrix for your, when your columns are zero mean. Okay. Okay. Okay, we'll start from here, then we'll go up. Okay. So what is principal component analysis that has been discussed in the lecture also. I'll just give you a very brief overview what it is. So what is principal component analysis? Let's say you have some data set given as x1, x2, xn, right? So what you want to do is you want to compress this data set into some k-dimensional data. So this is an n-dimensional data that you have right now. You want to compress it into k-dimensional data. So for that, what you do is you find some directions or the basis p1 to pk so that you preserve maximum information that is possible. Okay, so there are like similar definitions for this where you say that you want to minimize the covariance. So minimizing covariance would mean that you are not picking up related features, you are picking features that are far apart from each other. Okay. So also there is one more similar thing where the individual variance is maximum. Okay. So you can just remember that you should try to preserve the maximum information. Okay. So what is the way to do that? So let's say you have some data point x. So you have some data set with feature x1 to xn. Okay. So first step is that you should find its covariance matrix. Okay. You should find its covariance matrix sigma, that is 1 by n x transpose x, assuming that your x1, x2, xn has zero mean. If it does not have zero mean, you can very easily convert it to zero mean by calculating mean of every column and then subtracting it from that particular column. Okay. And after you have calculated the covariance matrix, next task for you is to find the eigenvalues and eigenvector for this particular matrix sigma. Okay. Then you should pick the k largest eigenvalues and the corresponding eigenvectors to these k largest eigenvalues are your features p1, p2, pk that you are looking for, that will preserve maximum information for you. Okay. And what is the representation of okay, so once you have found p1, p2, pk, you want to convert your data points, let's say x1, x2. So remember the feature had subscript over here. I'm using superscript. So let's say you want to convert your data points x1, x2 to now this k-dimensional features. What you can do is you can just take p1 transpose x1, p2 transpose x2 till pk transpose x1, and you will get the corresponding representation for your vector x1. I'll do this by an example. Right now I'm just explaining. Okay, so a very small recap. So when you have to find the principal component, first step that you will do is you will find the covariance matrix. If you have zero mean columns, then it is very simple, that is 1 by x and x transpose x. Then you will find the eigenvalue and eigenvector for this particular covariance matrix. Pick out the k largest eigenvalues and their corresponding eigenvectors. Okay, this is the task that you have at hand. Okay, so yeah, we'll do this example, but before that we can take a 5 minutes break because this is a long lecture and today we have a lot of content also to cover. So things might get a bit more for you. So I'll take a 5-minute break and we can again start at 7:10. By that time, if you have any doubt related to whatever we are talking till now, you can ask. After the break, we'll solve one question on finding this principal component for this particular example that you can see over here. We'll resume at 7:10. You can take a 5-minute break. If you have any doubt, till then you can ask. It's fine. Yes, Naman, there will be application of PCA when you do autoencoders and those kind of things. That's why I think professor is covering this concept. Okay, so Arun, can you please be a bit more specific what specific concepts you are trying to learn so that I can give you a better suggestion. So what topics are you trying to learn in statistics? Yes, so the dimension that are left have most information stored. So I doubt that you will find PCA explicitly in common statistics books. You can find it in a linear algebra book. This is one thing. Another thing is that if you want to learn these basic concepts like covariance and those things, you can refer to a book called, I'll type it out. So it is called Introduction to Probability and Statistics for Engineers and Scientists by Sheldon and Ross. You can refer to this book to sort of grasp the initial thing, and yeah, and then you can refer to some linear algebra book where you have this principal component analysis explained. Otherwise, you can search some YouTube videos also, like how does this preserve the maximum information. This proof is also there in the course lecture by professor. Like he has included a very straightforward proof. Once you are clear what is covariance matrix, what is variance matrix, then it would be very clear for you what proof he has done. Okay. So yeah, so like the method how you find PCA that I am covering today, that you have to find the covariance matrix. As I mentioned, if you just make your means 0, then covariance matrix is nothing, but you have to just find X transpose X and divide it by the number of data points that you have. Okay. Again, this is data points, not the number of features. This is the number of data points that you have. Okay. And then find the eigenvalue and eigenvector of this thing, and then find the k largest eigenvalues. This is how it can be done. Okay. So we'll try to do one example. There were more points. I have purposely removed the later on points. So this is a two-dimensional data, right? This is a two-dimensional data. We have 3 data points, right? And we have been asked to find the principal component. So we'll find the first principal component, because there are two. This is a two-dimensional data set only, so we can't go lower than 2, right? Okay. So first of all, I'll just try to write it in sort of this form. So my x is 2, y is 1, 3, 5, 4, 3. Okay. So one thing is right. So what is the mean of this particular thing? The mean right now is, this is 2, 3, 5, 4, 9 by 3. This is 3. Here also mean is 3. What we wanted is, we wanted our mean to be 0. So we'll, let's say, transform it into some x hat and y hat, where we subtract mean from every element. So first would become -1, 0, 1. Second one would become -2, 2, and this is 0. Okay. So we will work with this data now. We'll work with this data. Okay. So now, because this is a zero mean thing, so we can find our covariance matrix as 1 by 3 x transpose x. This is 1 by 3, and this is -1, 0, 1, -2, 2, 0, -1, 0, 1, -2, 2, 0. Okay. So just forget the 1 by 3 for the time being. What it would be? Should be 1 plus 1. This is 2, right? This would be 2 again, because this is 2, this is 0, 0. What is this term? This is 2, and the last one is 2 to the 4, and 2 to the 4, 8. So this is the matrix that we obtain, right? So we have obtained our sigma. What is the next task? Next task is to find the corresponding eigenvalue and eigenvector. Okay. I'm not going to explicitly find it. I'm going to use a software, that is MATLAB, to find eigenvalue for this, and I'll write straight away. So my A is, let's say, 1 by 3 2 to 8. Okay, sorry. Then let's say so I have obtained 2 eigenvalues over here. Okay. So if you solve, you can get lambda to be 2.8685. So you need not explicitly solve this right now. So this is 4648. I'm just trying to give you an idea, if you have some data set, how you can find its principal component. Okay. Now and the corresponding eigenvectors are, for this one we have 0.2898 and 0.9571. Okay, and for this we have minus 0.9571 and 0.2898. Okay, so we have to find the principal component. So what we said is that we'll pick the largest eigenvalues and the corresponding eigenvectors. So the larger eigenvalue among these two is this 2.8685, right? And the corresponding eigenvector is this. So my P1 becomes 0.2898 and 0.9571. Okay. Now, rather than saving my data in 2 dimension, what I can do is I can project my data points onto this P1 and save that, and that would serve my purpose. Okay, how would you project your data points? So for example, your first data point, this is 2, 1. This can be projected as 2, 1 transpose P, that is nothing but 2 times 0.2898 plus 1 times 0.957. So whatever you will get a number that will be a one-dimensional representation of your data point 2, 1. Okay, and this is how we do principal component analysis. If you would had multiple, let's say your initial data point was some 3-dimensional data point, and you obtained two principal components P1, P2, and you wanted to convert x, y, z, then x, y, z would have been converted to, let's call this point as, let's say, what can we call it? Capital X, right? Then it can be converted as capital X transpose P1 and capital X transpose P2. This is how you can project your data point to a lower dimensional space after you have found out the principal components. Okay. Okay, so there was one more question that I sort of skipped. So you are given the direction of principal components. So these two are your principal components, and you are given with a data point 1, 2, 3. It is asking you to project this data point 1, 2, 3 onto the space that you obtained using principal component analysis. So what it would be? So let's call this data point as X. So the projection would be X transpose P1 and X transpose P2. So this is 1 by root 2 minus 3 by root 2, and the last the second component would be minus 2 by root 2 plus 3 by root 2. So this is minus 2 by root 2, and this is 1 by root 2. So this is what you will obtain in 2 dimension. The projection of this point in 2 dimension is this, with respect to these as your basis. Okay. Any doubt? Any doubt till this point?
Sir,
Yes.
from eigenvector, whichever is largest, you have taken it as principal component, isn't it?
Yes.
You have taken principal component, that is sum of that all the elements you have to take. You have to consider sum of the elements, or how to take it, sir?
So the large or the small will be decided on the eigenvalues. So let's say we had two eigenvalues, 2.8 and 0.4. This is larger, and the principal component we will take is the corresponding eigenvector.
Oh, we have to take it from eigenvalue. Okay, fine.
Okay.
So that we will take it as principal component. Can you scroll down, sir?
Yes, sure.
After that principal component, how you have taken transpose of that value into principal component, sir?
Yeah. So principal component is by this vector. Okay, so I'll try to explain this once. I think that will be much clear. Okay.
Okay, sir.
So I think I didn't give enough motivation for this. That's the reason. I'll just try to explain it once more. So why we do first of all principal component analysis is, let's say we have some high dimensional data. Okay. We want to store it in some smaller dimension. Okay. Okay. Now, let's say, okay, so let's say you have some vector 1, 2, 3, and you have another vector 2, 3, 4, right? So what does this vector 1, 2, 3 and 2, 3, 4 means is, if you talk it from perspective of linear algebra, is this is 1 times 1, 0, 0 plus 2 times 0, 1, 0 plus 3 times 0, 0, 1. Okay. So what actually you do is, you know that your basis vectors are this. Okay. So this is your B1, B2, B3. And you save the corresponding component that you multiply with these vectors to obtain your final vector. Right. So this is one thing. Okay. Now, let's say you somehow know that that whatever values that you want to save, the first two component of that particular vector are same. Let's say you want to save vectors like this, 2, 2, 4, 2, 2, 3, or 1, 1, 2. So you just want to save vectors like this. Okay. So here what you required is, let's say you have m vectors to save. Okay. And these are all 3-dimension vectors. So you had 3 cross m number of values that you had to save. So you would have saved this 1, you would have saved this 2, you would have saved this 3, whenever you are saving this database. Okay. Now for this thing, what you can do is, you can choose a smarter basis. So let's say your basis is 1, 1, 0, okay, and 1, 1, 1. Okay, oh, sorry, 0, 0, 1. Okay. So now what you can see is, let's say you want to write this particular thing in form of this B1 and B2. Okay. How you can write it? You can write this thing as, this is 2 times B1 plus 4 times B2. Okay. So now if somebody asks you to save these values, what you can do is, you can just save 2 and 4, and you tell them that the basis that I'm using is this one. Okay. So you save 2 and 4, and the basis that you're using is this one. So this way, how many values you need to store? You just need to store 2 times of m, because for every vector you are saving only 2 values. Now remember one thing, when you want to recreate your vector, the vector that you will recreate is 3-dimensional, but the corresponding values that you are saving is only 2, because of the choice of basis that you have made, because your data set had some specific structure. This is another thing, just remember this. Now your data set over here had some very clear structure, that your first element is same as the second element. This might not be very true in real world. In real world, what we want to do is, that let's say whatever data set we have, rather than taking all the bases, let's say what you said is, I'll just ignore my second basis. Okay, let's say what you said is, I'll just ignore my second basis and I'll only save my one component. Okay, what will happen? You will have some error that you have made. So whatever you reconstructed only using one point, one basis element, and what you actually wanted to save, that will have some error now, because you have just ignored one of the bases. Okay, now what is the role of this principal component analysis? The role is to find such a basis, okay, that has minimum loss of information. Okay, so what I'm saying is, let's say my data set is in 3 dimension only, and it does not has any special structure. Okay, so my data set is in 3 dimensional, so it has some special structure, but it is not very visible to me. Okay, so it is a 3 dimensional, but I want to save it using only 2 cross m vectors. That is, I want to find 2 bases such that if I use these bases, I'll preserve maximum information. For example, in this case, your data set had some explicit structure. So using just these 2 bases, you were able to solve, you were able to preserve all the information. But it is possible that you might not preserve all the information, but you want to preserve the maximum information possible. Okay. So for that purpose, you have this kind of thing, this principal component analysis, the steps that we did. What we did is, we found one principal component. So this will act as my basis. Okay, so now this particular thing, 0.2898, 0.9571, this will act as my basis. Now I have 2 dimensional data that I want to store just using one component. Again, I want to mention that when you recreate your vector, so you have saved 2 and 4, but when you recreate your vector, you will get 3 dimensional vector only. Okay, only the number of terms that you want to save has reduced. Okay, now what I did through this dot product is, so let's say this is my basis. Okay, what is the term that I should be saving? Okay, what is that quantity that I want to save? That quantity is given by this thing, that is your whatever is your existing vector, it's transposed with the principal component that you have. That is, this is the projection of this thing in this direction. So this is the value that you will obtain, that you need to save. Okay, so this is what I meant. Am I clear? Was I able to make things clear why I was doing dot product?
Yes, sir. Yes, sir. Thank you. Yes, sir.
Okay, so any doubt in principal component analysis? Then we'll try to move to something known as singular value decomposition. I know this is pretty fast today, but we had 3 topics to cover, so this is the best I could do. So we'll move to singular value decomposition after this. Any doubt in this? Okay. So before moving into singular value decomposition, I'll try to give similar motivation. Okay. So one thing why people use singular value decomposition in deep learning, especially when you will encounter word embedding techniques, or for that matter graph embedding techniques, is that, let's say you have some matrix M, okay, which has dimension n. Okay, so dimension n means that you need to save at least n linearly independent eigenvectors. I won't say eigenvectors, but you need to have n linearly independent eigen vectors. Okay, just vectors, let's say. So the case can be either you have to find n linearly independent vectors, or you have to save n linearly independent vectors. But what your application demands is that you can get only some k linearly independent, you are allowed to save only k linearly independent vectors. Okay, so what is the k dimensional closest approximation to this? This is what you want to find. That thing is given by singular value decomposition. That we'll see how it is given, but that thing is given by singular value decomposition. This is one motivation for singular value decomposition. Okay, so I'll come to this whatever is written over there later on. Another motivation is when you had eigenvalues. Okay, first of all, eigenvalues is only defined for square matrix, right? Because if you want your ax to be lambda x, then your so the input and the output dimension of this linear transformation A should be same. Okay, so your A should be a square matrix. Now what happens to rectangular matrix? We have lot of rectangular matrices in practices. What can be done to them? Okay, so what we do is, let's say what we want is that I have some vectors v1, v2, vn, okay, which is a basis for let's say domain of A, and I have some u1 to un which is basis for range of A. Consider A as some function over here, right? Okay, so also one more condition is that this set is orthonormal in nature. So v1, v2, vn are orthonormal to each other, and u1, u2, un are also orthonormal or orthogonal to each other. Then does there exist such a vector that A of vi is some sigma I times u of I? Okay, so this is another or the first motivation that people use for singular value decomposition. What we want is, rather than having AB is equal to lambda b, we are restricting ourselves to be AB is equal to some sigma times u. Okay, so V's are also orthogonal on the domain side, and U's are also orthogonal on the range side. Okay, so right, this can be smartly written something as your A is, so you want to decompose your A into U times the sigma matrix and V transpose, where your sigma matrix is a diagonal sort of matrix. Why I'm saying diagonal sort of and not exactly diagonal, we will see to it. Your V is an orthogonal matrix. Okay, so orthogonal matrix means its columns are orthonormal. That would also mean that V transpose is identity, and your U is also an orthogonal matrix. Now let's look at the size of this matrix. What is size of U, what is size of sigma, and what is size of V? Now let's say A is m cross n. Okay, so for A into Vi to be well defined, what should be my dimension of Vi? Vi should be n cross 1, right? Great. Now also my Ui should be m cross 1. Okay, now my A is m cross n. Okay, so now let's see, so I have U. How many U's I want? I want n of them. Okay, so what is my dimension of U? U is, sorry, m cross n, right? Sorry, just a second. I'm making a mistake here. Okay, so this should be n and this should be m over here. So this should be m over here. Because it's not necessary that your domain number of like linearly independent vectors in domain and range are same. So your u should be m cross m. Your v should be n cross n, and your sigma now is m cross n. So that the overall product becomes m cross n, that is your matrix A. This is one thing. Now, how do we find our A and mu and sigma, sorry, mu, sigma and V transpose? So one thing that we can do is, let's say we try calculating AA transpose. What is AA transpose? This is U sigma V transpose, and okay, so when we take the transpose, everything flips. So this would be V sigma U transpose. Now, because this thing is my orthogonal, V is an orthogonal matrix, this would become U sigma square U transpose. Okay. This is something, okay, so AA transpose now is a symmetric matrix. Because A was some matrix and we took A into A transpose, this is always a symmetric matrix. So when we obtained this thing, if you recall, when we talked about eigenvalues and those things, okay, I told you that if you have a symmetric matrix, then I didn't tell you, I think. Okay, so if you have your symmetric matrix, then P inverse is nothing but your P transpose, because the vectors that you obtained are orthogonal to each other. Okay, I think I mentioned it over here. So when your A was PD P inverse, you can replace it by PD P transpose for symmetric matrices when you are doing eigen decomposition. Okay, so let's get back to our story on singular value decomposition. So this is similar to the eigen decomposition that we had. Okay. So what we can say is that we can obtain P. How did we obtain P when we were doing eigen decomposition? These were eigenvector of this particular matrix. So we can obtain U by stacking eigenvectors of AA transpose in form of a column. Okay, and we can obtain sigma square as the eigenvalue matrices, right? And then we can obtain sigma by just taking the square root of all the diagonal elements. We'll see with the help of an example, that will be more clear. And similarly, when you have A transpose A, this is your V sigma U transpose, U sigma V transpose. This is nothing but V sigma square V transpose. Okay. So this, from here we can infer that V is nothing but matrix of eigenvectors of A transpose A. Okay. So whenever you want to find the singular value decomposition, you will do two things. First of all, you will calculate AA transpose, find its eigenvalue and eigenvector, use it to obtain U and your sigma square, and then you can calculate A transpose A to compute your V matrix. Okay. There is also some short trick to calculate V that I am not mentioning over here. For that, if somebody is interested in how we go about singular value decomposition, one resource I can refer you to is, there is a lecture by Gilbert Strang. So Gilbert Strang is a great linear algebraist, probably the best that is alive today. So you can look at his lecture on singular value decomposition. It's a very good lecture. you'll get a lot of insights from it. But right now I'm just telling you that this is one way by which you can find your U, sigma, and V transpose. There are some short tricks. For that you can look at this lecture. It's available free on YouTube. Okay. Okay. So this is one thing. Okay. So, okay, what are singular values? Now there is something that is known as singular values, because of which this is known as singular value decomposition. Now, as I mentioned, when you do your A transpose A or AA transpose, right, you will obtain sigma square. Okay. So the eigenvalues, let's say for this AA transpose A or A transpose is lambda 1, lambda 2 till lambda n. Then the square root of this lambda 1 to lambda n, let's say this is sigma I 1, this is sigma n. This sigma 1, sigma 2, sigma n are known as singular values. Okay. We would skip this question for the end. Okay, let's not skip this question. We'll try to solve this question. Okay. Yeah, I'll solve this question. Quickly we'll solve. Okay. So we want to find the singular values for this particular matrix. Okay. So first step that we should do is we should find A transpose A. This is what is written over here. Okay. So what is my A transpose A? This is -4, -7, and this is 1, 4, right? This is -4, -7, 1, 4. What is A transpose A? Can somebody tell me? I'll use the MATLAB to find. I'm not doing calculation because of time. This is -4, -7, 1, 4. A transpose. This is A transpose into A. This is 17, 32, 32, 65. Okay, so this 17, 32, 32, 65. Okay. So I'll try to find the eigenvalue also for this. So the eigenvalue that we obtain for this, again using the same thing that we will do A transpose A minus lambda I is equal to 0, you will equate this determinant to be 0. The values that you will obtain is lambda is equal to 1, 81. Okay. So what we said is that the singular values are square root of these eigenvalues that you will obtain for A transpose A. Okay. So sigma 1 is, let's say, 1 and sigma 2 is 9. So we'll obtain this as the correct answer. Okay. Okay. We'll do okay. Yeah. We'll do one example of SVD from scratch. Okay. So this is the matrix that we have. We have A to be 3, 2, 2, 2 minus 3 minus 2. We want to find the singular value decomposition for this. Okay. Now, as I mentioned over here, to obtain U, we will first have to do AA transpose. Okay. So let's first of all do AA transpose. And what is the value that we'll obtain from AA transpose? So A is 3, 2, 2, 3, 2, 2, and 2 minus 2, 3 minus 2. So the value that we obtain is 17, 8, 8, 17. I have just skipped the calculation for time. Okay. So let's call this matrix. So we want to find the eigenvalue and eigenvector for this particular matrix. Okay. So what we will do is AA transpose minus lambda I is equal to 0. So this would mean 17 minus lambda, 8, 8, 17 minus lambda is equal to 0. Okay. So what does this imply? This is 17 minus lambda square minus 64 is equal to 0. So this is lambda square plus 17 square. What 17 square? It is 289, right? So plus 289 minus 34 lambda minus 64 is equal to 0. Okay, this is lambda square minus 34 lambda, and this is plus 225 is equal to now is equal to 0, right? So this would again give me lambda square minus 25 lambda minus 9 lambda plus 225 is equal to 0, which we can again write lambda minus 25 minus 9 lambda minus 25 is equal to 0. Okay. So now lambda, sorry, this is not lambda square, this is just lambda. Okay. So lambda is equal to 9 or lambda is equal to 25. This is the value that I obtained. So the eigenvalues for A transpose that I have obtained is 9, 25. So what is the singular values that I'll have? So singular value is 3, 5. So sigma 2 is 5, sigma 1 is this. Okay. Now let's obtain eigenvector corresponding to this. So for lambda is equal to 9, what is my eigenvector for A transpose? So this is 17 minus 9i. So this is A transpose minus 9i V is equal to 0. So this would be minus 8, 8, 8 minus 8, V1, V2 is equal to 0. This implies that my V1 is equal to V2, right? Also, I mentioned that this V1, V2, Vn that we have should be orthonormal, right? So we will sort of try to, so one choice for this is 1, 1, but we'll further normalize it. So this would become 1 by root 2, 1 by root 2. Now for lambda is equal to 25, what we have? We have, just give me a second. So this is my A. So this would be, okay, I'm sorry. So if I had 17 minus 9, this would have been plus 8. This is also plus 8. So this would mean minus V1 is equal to V2. So this is minus 1. There should be a minus 1 over here. If I subtract 25, then it will be minus 8, 8, 8, minus 8. V1, V2 is equal to 0, or V1 is equal to V2. And we will obtain 1 by root 2, 1 by root 2. Right. Now let's look at the dimension that we had. U is m cross m. Okay. So here it is 2 cross 3. So U should be 2 cross 2. So we have obtained our U. So U is 1 by minus 1 by root 2, 1 by root 2. We are writing this vector over here in the column form over here, right? So this thing, we are writing it as a column over here. Okay. Now again we will have 1 by root 2 and 1 by root 2. Okay. Now what was my sigma? Sigma was m cross n. So this should be a 2 cross 3 matrix. So we have 2 rows and 3 columns. This is what we want to fill. Okay. As I said, it's a sort of diagonal matrix where the diagonal entries are singular values. So we have 2 singular values, right? One is 3 corresponding to lambda is equal to 9, and then there is 5 corresponding to lambda is equal to 25. So we will have 3 over here, 0 here, 5 here, 0 here. This is 5. I'll just write it here. So the rest of the entries that you have left in the rectangular matrix, you just fill it in with the 0. Okay. Now the only thing that we have left is V to be calculated. Okay. To calculate V, what should we do? to calculate V, we should have, earlier we had A transpose, now we should have A transpose A, and this is given by, I'll just use, so this is 13, 12 and 2, 12, 13 and minus 2, and 2 minus 2, this is 8. Okay, so this is the matrix that you obtain. Okay, now if you find the eigenvalue for this particular matrix, okay, I'll try to find the eigenvalue for this thing. So this is A transpose into A. So the eigenvalues that you obtain is lambda is equal to 0, then lambda is equal to 9, and lambda is equal to 25. You see that these are matching with the ones that we obtained before, right? So now we can find eigenvectors also, right, corresponding to the same eigenvalues. So for lambda is equal to 0, we obtain this is just give me a second. You obtain this value to be minus 2 by 3, okay, 2 by 3 and 1 by 3. This is one that you obtain. For lambda is equal to 9, you obtain, I'm not sure what it is in terms of fraction, but what I have obtained is 0.2357. This is minus 0.2357, and this is 0.9428. For last one, I have obtained minus 1 by root 2, minus 1 by root 2, and then a 0. Okay. So now we want to write the V. So we should write it in the same order again. So first we should write corresponding to 3. So this would be 0.2357 minus 0.2357 and then 0.9428. Okay. Then corresponding to lambda is equal to 5. This is minus 1 by root 2, minus 1 by root 2, 0. And at the last, whatever is left, we'll write. This is 2 by 3, this is 1 by 3. I'll just verify using wait. Okay, so this is same that we obtained, and the MATLAB is also returning the same answer. So this is how you can do SVD decomposition of any rectangular matrix. Okay. Any doubt in this